If you are an aviation maintenance technician student, this is one for you. We're doing a deep dive into Chapter 14, Aircraft Fuel Systems.
And it's so much more than just holding fuel.
Oh, absolutely.
Yeah.
The real mission here is delivering perfectly clean, precisely measured energy and doing it under some truly extreme conditions. This is the life support system for the engine.
And right from the start, you have to understand that these systems are shaped entirely by, well, by extreme regulations. The FAA and other agencies demand absolute assurance of continuous power.
So give us a feel for how intense that gets. What's the kind of worst-case scenario they have to design for?
It's all about water. A turbine fuel system has to be able to run, and I mean run without interruption, even if the fuel is already saturated with water at, say, 80 degrees Fahrenheit.
Okay, so it's already maxed out on moisture.
Exactly. And then on top of that, you introduce an extra 0.75 cubic centimeters of free water for every single gallon.
Wow.
And then you cool the whole mixture down to the most critical icing temperature you'd expect in flight. And it still has to work perfectly.
Wait, hold on. You're saying the system has to function with fuel that's full of water, plus has slugs of extra water in it, and it's all freezing?
Precisely. That one requirement dictates almost everything else. Fuel heaters, pump design, where you put the sumps.
So the main goals are pretty clear then.
Yeah, three things. Uninterrupted supply, a clear fuel quantity indication for the crew, and safety. Isolating fuel in an emergency and minimizing hazards in a survivable crash.
It really is a complete life support system. Let's dig into the fuel itself, especially for reciprocating engines, because that's where the chemistry can go wrong really, really fast. We're talking about detonation.
Detonation is probably the single most violent thing that can happen to an engine, short of it ingesting a foreign object.
It's not just running rough.
No, not at all. A normal combustion event is a smooth, controlled burn that pushes the piston down. Detonation is a rapid, uncontrolled explosion. It's the fuel-air charge just combusting all at once from heat and pressure.
Often before the spark has even finished its job.
Exactly. And the consequence of that explosion is just brutal. It sends this massive shock wave across the piston, hammering the pin, the connecting rod, all the way to the crankshaft.
Just undirected violence inside the cylinder.
And if that keeps happening, it will destroy the engine, period.
So what are the precursors? What could an AMT overlook that might lead to something like that?
You have to look for things that cause surface ignition and pre-ignition. Basically, hot spots inside the combustion chamber.
Like what? Carbon buildup?
A sharp deposit, yeah, or maybe a cracked spark plug insulator that's just glowing red hot. These little spots ignite the fuel way too early in the cycle.
And that early ignition jacks up the pressure and temperature.
Far beyond the design limits. And that pre-ignition is what leads directly to that destructive detonation.
So the whole anti-knock rating system, the octane number, is really just a measure of the fuel's ability to resist exploding like that.
That's it. The whole system is based on a standard mixture of two hydrocarbons. Isooctane, which is very resistant, and heptane, which is very prone to detonation.
So 100-octane fuel acts like pure isooctane.
Correct. It performs just like 100% pure isooctane under test conditions.
Okay, so since we work on everything from little trainers to huge jets, fuel identification is where safety starts for the technician, right? You can't mix these up.
Absolutely non-negotiable. You have to be positive what fuel you're using. For AVGAS, we have the color codes to help.
Right.
100LL or low lead is blue. The older 100-130 is green, and if you see 82UL, that's unleaded, and it's purple.
But the big one is jet fuel.
The crucial thing to remember is that all grades of jet fuel are either colorless or kind of a light straw color. There's no dye.
And thankfully, there's also a physical safeguard built in at the pump.
Yes, and it's so simple. The nozzle for a jet fuel pump is just too big. It physically won't fit into the smaller tank opening on an AVGAS aircraft. It's designed to stop that catastrophic error from ever happening.
Okay, so we've got the right fuel. Let's talk about where it lives. There are two really different ways tanks are built, and that changes everything for maintenance.
It does. You've got rigid removable tanks, and you've got integral tanks.
So the rigid ones are just what they sound like?
Pretty much. They're separate containers, usually aluminum or sometimes turniplate, which is just coated steel you see in old planes. They're held in place by padded straps. The key thing is, the airframe doesn't rely on the tank for strength.
Which makes maintenance, I imagine, a lot easier. You can just drop the tank out and work on it.
Exactly. Now, compare that to an integral tank, which everyone just calls a wet wing.
Right.
On a big transport jet, the wing structure itself, the spars, the ribs, the skin, it's all sealed up with a special fuel-resistant sealant. The wing is the tank.
Which is great for saving weight and maximizing volume, but If you get a leak, you're not just swapping a tank. You are going inside the structure of the airplane.
And that's why the internal design is so important.
Hmm.
In those long wings, you have to stop all that fuel from sloshing outboard during a turn.
Because the pumps are all inboard, near the fuselage.
Exactly. If the fuel runs away from the pumps, they run dry, and the engine quits. So you have baffles.
And baffle check valves, right?
Yeah. Yes, those are critical. They're basically one-way doors. Fuel can flow inboard toward the pumps, but they slam shut and stop it from surging back outboard. It guarantees the pumps always have fuel.
We also see things like surge tanks on bigger aircraft. What's their purpose?
Surge tanks are interesting. They're usually empty cavities way out at the wingtip. They're there for overflow and venting.
So if the fuel expands in the heat on the ground,
That's one reason. It expands, flows into the surge tank, and then a little check valve lets it drain back into the main tank later. It lets the whole system breathe without spilling fuel overboard.
all this amazing engineering, and yet the biggest headache for an AMT is usually just water.
Water is the most common contaminant, hands down. It gets in mostly through condensation.
Just from temperature changes.
Right. You fuel up on a cool morning, fly up to altitude where it's freezing, then descend into a warm, humid environment. The airspace in the tank breathes and water condenses out. And since water is heavier than fuel, it settles right down into the sumps.
And filters don't really get it out.
Not easily, no. That's why sumping the tanks before a flight is so critical. You have to draw a sample from the lowest point.
And what are you looking for?
You want it to be clean and bright. If that sample looks cloudy or hazy, you have a problem. That's water. And you have to keep graining until it comes out clear.
Okay, so let's follow that clean fuel out of the tank. Let's get into the dynamics, the pumps. On big jets, it starts with a centrifugal boost pump.
Right. These are usually electric pumps submerged in the tank. Their main job is to provide positive pressure to the engine-driven pumps.
And that's to prevent vapor lock.
That's the whole game, especially at high altitude, where the low air pressure makes it easier for fuel to boil and form vapor bubbles. The boost pump keeps the fuel under pressure and in a liquid state.
And sometimes they work with an ejector pump, which is a really clever piece of kit.
It's brilliant. An ejector pump has no moving parts. It just uses the Venturi effect. It takes some high-pressure fuel from the boost pump, shoots it through a nozzle, and that creates a low-pressure area that sucks more fuel from the tank towards the pump inlet.
So it keeps the main pump fed even when the fuel level is low.
Exactly. It's totally passive and very reliable.
Now, for piston engines, the main engine-driven pump is often a vane type. What's the key thing to know there?
Vane pumps are constant displacement. For every revolution, they move a set amount of fuel, but engine speed changes all the time, so it's often pumping way more than the engine needs.
So it needs some kind of internal regulation.
It needs two critical valves. First is an adjustable pressure relief valve, which just sends any excess fuel back to the inlet side of the pump.
And the second one?
Is the bypass valve. This is just as important. It lets fuel flow through the pump if the pump isn't working, like during an engine start when you're just using the electric boost pump. It prevents fuel starvation.
Okay, so pumps move the fuel, but valves direct it. And with valves, position indication has to be crystal clear.
It is a life or death issue. On a small plane, you might have a handle with positive detents. You can feel it click into position.
But on a jet?
On a jet, it's all remote. You need annunciator lights, or on a modern flight deck, a graphical display on a screen like an eCam that shows you if a valve is open, closed, or critically in transit between positions.
What are the common types of manual valves an AMT would see?
In light aircraft, you see a lot of cone or plug valves, also poppet valves. For bigger planes, for things like firewall shutoffs, you'll see a really robust gate valve.
And when they're not manual, they're actuated.
Right. Motor-operated valves are common for large valves out in the wing that need a lot of torque. For faster-acting safety systems, you'll often see solenoid-operated valves, which are basically just electrically triggered poppets.
And this all gets connected by fuel lines, rigid aluminum or steel flexible hoses. But there are some installation rules here that are absolutely critical.
They are. With the flexible hose, you always use the printed ley line to make sure you haven't twisted it during an install. But the number one rule every AMT must know is this. Fuel lines are always routed below electrical wiring.
Always. Why is that so non-negotiable?
Gravity. If a fuel line leaks, you want the fuel to drip down and away. If it was above an electrical wire bundle, it would drip onto the wires. That could cause a short, an arc, and turn a tiny leak into a massive in-flight fire.
Simple physics preventing a catastrophe. And speaking of electricity, what about the static charge from fuel just flowing through the pipes?
That's a real thing. Fuel moving generates static electricity. To stop a charge from building up and causing a spark, every single metal component, tanks, lines, filters, has to be electrically bonded together and grounded to the aircraft structure. It gives the charge a safe path to dissipate.
Let's shift to maintenance. You're an AMT, you find a leak. The first thing you have to do is classify it, and there's a very specific system for this.
There is, and it dictates what you do next. It's all based on the size of the wetted area after 30 minutes of observation.
Okay, run us through the classifications.
The smallest is a stain, less than 3/4 of an inch in diameter. Then you have a seep, which goes from 3/4 of an inch up to 1.5 inches.
Getting bigger.
A heavy seep is next, from 1.5 up to 4 inches. But the most critical one is a running leak. That's when fuel is actually pooling and dripping off the aircraft.
And a running leak grounds the plane?
Immediately. No questions asked. That requires immediate repair.
And if that repair involves something like welding a tank?
You have to assume it's a bomb. Any tank must be completely purged of all fuel vapors before you put any heat near it. Use steam or hot water or fill it with an inert gas to displace all the oxygen.
And what if the job is entering an integral tank on a big jet? That seems like one of the most hazardous jobs there is.
It is. The safety checklist is long, and it's mandatory. All aircraft power off, breakers pulled. You can only use approved explosion-proof tools and lights.
And personal protective equipment.
Non-static clothing, a proper respirator. You need a continuous flow of fresh air being pumped into the tank, and you're constantly monitoring the air inside with a gas detector.
And you can't go in alone.
Never. You must have a trained, dedicated standby observer stationed right outside the tank opening the entire time. That person is your lifeline.
Wow. That level of procedure really tells you how high the stakes are.
It does. And maybe the highest stakes come from a misfueling error. Let's say someone puts Jet A in a piston engine aircraft, and the engine gets run.
What's the recovery for that? You can't just drain the tanks, can you?
Oh, no. It's a massive job. If the engine ran, you have to drain and flush the entire system, tanks, lines, carburetor, everything.
But the damage could already be done to the engine.
That's the fear. So you have to do a compression test on all cylinders. You have to do a bore scope inspection, looking right at the tops of the pistons for damage from detonation.
Because the jet fuel has such a low anti-knock rating?
Exactly.
Yeah.
You also have to drain the oil and cut open the oil filter, looking for any metal, which would be a sign of internal damage. Only after all that and a full, clean engine run-up can the aircraft be returned to service.
This has really covered the whole spectrum of this chapter, from the chemistry of detonation all the way to the life-or-death procedures for tank entry. The AMT really is the guardian of this entire system.
And it comes down to understanding how all the pieces connect. Think about that little vane pump. It has two fail-safes, the relief valve for overpressure and the bypass valve for pump failure. Small parts, but they prevent a total loss of power. It's all about that built-in redundancy.
So here's a final thought for you to chew on. Given how complex modern fuel indicating systems are, with capacitance probes and mass flow sensors giving the crew precise data, how profoundly does a pilot's situational awareness, their ability to know if they can make it to their destination, depend on the proper function of a single electrical wire harness going into that fuel tank? That's where the human responsibility and the machine's complexity meet.